Hello, we will continue talking about folding of sectoral structures. We will do two examples just to make the concept a little bit more clear. So we have the sectoral structure shown here. AN equals to 212 subscript 5, and we have its geometric representation shown. And we're going to do a few folding operations on it. So the first one we have is U4 of AN, which means unfolding the fourth joint. So we start counting from the L prime end here, and we count four joints, and then we reach this joint right there, and we unfold it. And this gives us the sectoral structure 2, 1 cubed subscript 5. The next example is F subscript 2 or F2 of AN. So that means we're going to count 1, 2, and we're going to fold this joint. And this will give us 3, 2 subscript 5. The next example we have is combining these two operations. And notice when we have a plus sign, that means we're going to do these simultaneously. So we will say U4 plus F2 of AN. So that means we will be folding this one and unfolding this one, and we're going to get 3 1 squared subscript 5. Next, we're going to do the random joint operations. So first we have here, we have unfold alpha of AN. So this just means we're going to unfold any alpha joint without specifying which one. So usually we get multiple solutions. However, in this particular case, both solutions will be identical because it's a symmetric sectoral structure. So basically we can either unfold this one or that one, and under reverse symmetry we get the same result, and therefore the result will be 2 1 cubed subscript 5. Now let's do random unfolding of an alpha plus a folding of a random beta. So in this case, again, because there's a plus sign, that means we're going to do the two actions simultaneously, not sequentially. So therefore, we have two possible solutions. We could either unfold, let's say we unfold this one and fold that one, we get the solution 2 squared 1 subscript 5. Or we can fold this one and unfold that one, and we get 3 1 squared subscript 5. And you can double check, if you do all the possible combinations, they will always be one of these two solutions. Now here we have a more complicated example right here. So this is two sets of sequential actions. So the first one, we start reading from right to left for the sequential action, is folding a random beta and unfolding a random alpha. And at the same time, we will also unfold two alphas. So if we do this, it's really, what it really simplifies to is one beta folding and two alpha unfoldings. And that ends up giving us the xi structure 1 to the power of 5 subscript 5. So if we think about it, we're gonna fold one of the beta joints, either this one or that one, and then we're gonna do 3 unfoldings. So we will really undo the folding we just did, and then we will also unfold these two, and then we get a maximally unfolded structure, which is a xi structure. Now, we want to recall a few things here. So for any sectoral structure AN of, and this is what we're looking at right now, of degree n and order lambda, if we do random alpha random alpha unfoldings um, a number of times, we will turn it into a xi structure because we will unfold every beta, every alpha joint. Now the question is what is the minimum number of unfoldings we need to do? And that will be really the number of alpha joints. And we know that the number of alpha joints is equal to n minus lambda, so the degree minus the order. So therefore, we will say u alpha to the power of n minus lambda of an gives us xi n. Now for the same sectoral structure, how many foldings, how many beta foldings do we need to do to turn it into a theta structure? And that would depend on the number of beta joints, which we know is equal to 1 less than the order. So we will say f beta to the power of lambda minus 1 of an gives us theta n. Here we're going to look at the polynomial, or the folding polynomial, or maybe the folding algebraic expression is a better way to call it. So we have this example, an equals 421 squared subscript 8, and we see its geometric representation. And we want to fold it, or we want to change it into the structure shown on the right, which is 2 cubed subscript 8, and that is Bn. Now, in order to do that, just by looking at the diagram, we need to do two things. First, we need to unfold this particular alpha joint, so the second joint, and then we also need to fold this one, the seventh joint, which is a beta joint, and then it becomes that one. And now we see that any two sectoral structures of the same degree can be folded and unfolded into each other. That's why we say they are homeomorphic or discretely homeomorphic. Now let's express the polynomial, the folding polynomial. So O an, so the folding of OAB, so the folding of A to B is equal to, we said we're going to go to the second joint, so x minus 2, and we will unfold it, so to the power of -1, times we go to the seventh joint and we fold it x minus 7. Now, of course, if we want to go from here to there, we have to simply reverse these polynomials. So OBA will be equal to really the reciprocal expression. So it will be x minus 2, which means folding the second joint, and we can see that right here. And then x minus 7 to the -1, that means unfolding the seventh joint, which is this one, and that takes us back to where we started. So notice that OAB is really the reciprocal of OBA. We can also call it the folding inverse. So OAB to the -1 equals OBA. If we multiply these two together, the fraction will reduce to 1. And this is why it's nice to use these folding algebraic expressions or polynomials, because they really give us a way to turn this into real algebraic equations. Now, notice one thing, that OAB squared, this is where it's very interesting. So if we're simply going to square the algebraic expressions, this should become a -2 and this should be a 2. So everything is squared. However, it gives us the same result. Because if once a joint is unfolded, if you unfold it again, it doesn't change. and once a joint is folded, if you fold it again, it doesn't change. So this is how where it's a little bit different from simple algebraic expressions. So OAB to the power of n is the same as OAB in this case. Now, where it may not be the same, or where it really becomes helpful to keep track of the powers, is if we're doing many operations. So not just this simple operation. So let's say we're doing OAB and then we're gonna square it and then we're gonna do many other operations, then it could make a difference. Now, if we have a third diagram, so let's say we're gonna go from here to another diagram and then back here, and each of them has its folding expression, we can say that OAB is equal to OAC times OCB. So if we have a figure here, C, we go from A to C and from C to B. If we find the polynomial here and the polynomial here and we multiply them, it should give us the same result as going directly. What else? So additionally, here we're gonna see this F0 or FO, either way. So this means when you see this, it means folding one of the expressions within OAB. So that's why we have a naught, F naught, or F0. Similarly, if you see U0, that means you're unfolding specifically within the operation OAB. So in this example, we have OAB is equal to x minus 2 to the negative 1 times x minus 7. If we further multiply this by F0, that means we will fold or we will cancel the unfolding expression here, one unfolding expression, which is this one. So this would simplify. So F0 of OAB would give us x minus 7. And similarly, if we say U0, that means we're going to cancel one of the folding expressions. So here we have x minus 7 is folding, we cancel it. So this simplifies to x minus 2 to the negative 1. Now here we're going to look at another example, which is again from right to left, OAB, F0, OBA. So basically we start with OAB, which is x minus 2 to the negative 1 times x minus 7. We cancel the one of its unfolding operations when we multiply it by F0. So this cancels this expression and we're left with x minus 7. But now we also want to apply this one here, OBA. So that means the x minus 7 cancels with the x minus 7 to the negative 1, and we are only left with x minus 2. So that is the final answer. And this is the beauty of working with these polynomials, is that the answers they give you are all real geometric or have real geometric meaning.